I guess we're going to go ahead and get started with our session 5 panel. So the title of the panel is Challenges and Opportunities in Supporting Heterogeneous Architectures and Programming Paradigms for Exascale Computing. I'm Ron. We have a very distinguished set of panelists. Tony Schellen from UTC, Rajiv Thakur from Argonne, Howard Pritchard from Los Alamos National Lab, sorry. The tri-labs always abbreviate. I think we know where LANL is, but Pori tells me we have no shortage of questions for this particular topic, but we should probably start with each panelist making us an initial statement about what they think and feel on this topic. So take it away.
I think is it better to say seated or just stand up? Okay, I'll fight. First of all, just everyone hear me here okay? Mike? Okay, so Curry volunteered me for this last Thursday. So I kind of winging it. And like I was just telling Tony and Rajiv here, so owing to some excess.
You don't like me?
Oh,
sorry.
That's okay.
Corey told me to stand behind the podium. So
chewing up a little time, so we won't have to answer that many difficult questions, and maybe the test will be shorter. At any rate, so I've been talking with Aristotle there. We had a good conversation over lunch, and one thing I should say is that I have two hats, and that's the reason why maybe some of the things I thought about for this topic might be a little different from maybe others. But my hat that I think is more important is actually I'm the leader of an applications readiness team at Los Alamos, and our job is to get our multi-physics codes ready to go on new architectures as they come in. So it's not like the way out in the future with how many qubits are we going to need to solve this particular problem, but it's more like next year or 2 years from now, we're going to have this new system, and how are we going to at least be operational, if not performant? And so my focus typically has been more on application stuff. And recently, and some things Tony and I and Curry have been doing some work on some stuff, which actually I think is applicable here. So one of the things I think, at least into the medium-term future, which I think will be a challenge for these heterogeneous systems, actually for some of our evolving workflows, and this is no news to Livermore, is I think we're going to increasingly see these complicated workflow-based applications where there are multiple components to the workflow, and it's not so much we need to do some hero calculation on 2,000 nodes and never able to reproduce it again. But it's more like, for instance, a machine learning driven iterative workflow process. And we particularly are seeing this in the material science area where we need to get more accurate models for materials when they're in unusual physical states. And those actually, often these workflows, parts of them work better on, for instance, accelerator GPUs. Other parts work better on scalar processors. And in the future, there may be some others. And I think that will be, and if you look in the literature on all the various things, and you talk to people like at NERSC, and they have their own where data acquisition is involved in it as well. So they'll have the special nodes at the edge, for instance, that will acquire the data, feed it into the back-end compute backplane, which in turn has processes that, in a large workflow, again, where some are better working on GPUs. In the future, maybe some that really benefit from HBM on some nodes. And I see that as a major challenge. And if you look like at the work done with Flux, some other of these advanced schedulers, even in their current state, they have a lot of work that needs to be done to make them work better with heterogeneous models. So for us, I mean, we've been working in a hack group, right, for several years, longer than that, on all the issues with our software working on these heterogeneous platforms focus mainly on GPUs. But getting back to what Ron was talking about, there's another aspect too in the near future. Well, we already have these intelligent NICs, and there'll be more of them. And how are we going to use those? And I consider that part of this heterogeneous architecture too. Those might be, for instance, perfect for active message type stuff, where you don't want to get. They may have tight connections to the network. So even if we have a CXL, that's not going to take that problem away. And CXL brings its own problems anyway. Let's see. Okay, I talked about intelligent NICs. Oh, yes. Okay. And then the other one, it's not really so much heterogeneous, but there is this vision or dream that if we can build large systems with like a RISC-V or RMAC architectures, that maybe we can get little widgets via co-design that we can put into some of them that we do like magic for accelerating gather, scatter to HBM memory. And that's not quite heterogeneous, but it is sort of, because maybe you don't want to have too many of those. So it would present the same type of challenges in terms of job scheduling and stuff that we see with what we're probably thinking mainly about.
Okay, thanks, Howard.
No, I don't have slides.
Can you hear me?
I have them here, but I was also told that we won't need to make an opening statement, so I don't have one really prepared. But I mentioned some things yesterday that had we known 5-6 years ago that there would be so many accelerator-based systems today, we could have focused on that in MPI itself and had a better story right now. There's several proposals that the accelerator working group is considering and discussing, and something will come out of that. But we lost a few years because we didn't know. But going forward, we can expect more of heterogeneity on the nodes and more specialization, specialized accelerators, AI accelerators, and we somehow need to incorporate them into a solution for node programming, and also interoperate with the variety of node programming models that exist today. There's, as I said yesterday, OpenMP, OpenACC, SYCL, CUDA, HIP, and of course Cocos Raja, and I could be forgetting a couple of others. So there are so many in use by applications, and MPI needs to work work well in a hybrid programming model with these programming paradigms.
Thanks, Rajiv. Tony?
So I think I'm quoting Corey when we say that when we got to Exascale, we got there with COTS parts, and it's a GPU and a CPU and a bunch of them. And we're in a fast network, and they just cranked it till they got to Exascale. And the integration in terms of understanding the heterogeneity in that node is still pretty weak. So we have programming models that's essentially been pointed out that when you pick a programming model, let's say you pick OpenMP, for example, that's great on the node, or you pick Cocos as an abstraction. It includes OpenMP and CUDA underneath. Then MPI is thrown in. So VPC++ is sort of like, you have a model of a star where everything's quantum except for gravity, and it doesn't work together. So we're fundamentally a couple of things. We're clearly going to be using heterogeneity. Work on another project that we didn't talk about at this meeting, where we're doing everything accelerated, but all FPGAs in the network, FPGAs in the endpoint, understanding how to offload MPI. And we're not looking at the programming models the same way. We have MPI there, but it's essentially a DSL. We have a way of describing OpenMP, where you could use another notation for the concurrency, and it's being translated. And what ends up happening is you conserve the ideas, but you end up doing, maybe a bunch of compilation and optimization. You get that to move down the computation hierarchy into these new devices. So there's two different worlds I see going on the FPGA side, where we think we're going to have heterogeneous architectures and we can control them. Completely different ideas than what happens, let's say, in the hack group, or as we see the beginnings of having NICs on GPUs. Clearly convergence will happen of, there's going to be parts of the GPUs. We're going to have programmable network controllers. But whatever programming models we have, and I'll try to be brief here, clearly we're going to have to figure out how to make it be fast before we figure out how to make it be performance portable. We're dealing with awful performance, large fractions of the code time spent in MPI in GPU computation, where it used to be small fractions, painful effects. And so just keep in mind, these programming models aren't shown to work well together, except maybe some special cases. We have to figure out how to do it well by hand before we decide what to standardize or improve or generalize. So that's my feeling. We're going to be more heterogeneous, as the other panelists have said, and we don't really know how to make it work well together, except in special cases. I think you saw some of Patrick's comments on that.
Okay, thanks everybody. I have questions, but I'll hold off on them because this is supposed to be a audience participatory part of this. So do we have any questions from anyone in the audience? Just to get things started. Okay, you guys are terrible. So let me ask this question. So we have, at this point, we've had heterogeneous systems in HPC for 10 years, right? If you look at initial explorations around GPUs, and Howard could go back to the Roadrunner machine at Los Alamos that had was a heterogeneous machine to break a petaflop. We've sort of settled in on this on-node programming model, off-node programming model, right? And the questions that we've all been asking over this last decade are, what's the on-node programming model? Because most people assume the off-node is MPI. Is that trend going to continue? Are we going to have, a composition of multiple programming models, or are we going to have something else? Thoughts on that?
Well, the other problem of having something that a compiler could translate into a distributed memory code has not been solved yet, even for just CPU case. I mean, independent of accelerators, and that has been a tough problem going back decades. I remember high performance Fortran in the 90s was supposed to solve that problem, and the compilation challenges were too hard, so that didn't go anywhere. There could be other solutions like Legion, for example, could be a unified model, and it's being used in some solutions, some applications. But at least in the near term, or in a 5-year time frame, we will see a composition of maybe even 5 to 10 years, a composition of programming models.
Ron, I would say as long as there's a significant advantage to managing movement of data yourself, you're not getting rid of MPI. So that's the first thought. So how could I get rid of the advantage? I could slow things down other places, which wouldn't make any sense. I think we'd have to figure out some way that there's a locality-based movement of data. And somehow I don't think let me put it this way. When we use MPI on node, we're making a mistake. That's, for example, on a regular, we'd like to do that faster than that, right? There's all sorts of pretty legacy stuff. Like we have a full operating system, we have abstraction barriers, we have all these extra pieces. But at least on node, we could get down to 0 copy if we work hard enough. Now, GPUs clearly have lots of hierarchy in them when they're inside a server, inside a half of a server, a root, a complex, and obviously on the network. So all that hierarchy we want to account for because we want performance. I guess I still want to be able to control when and how my data moves, or at least actually maybe I'd like to control more about how and when my data moves than I can do now, not less. So I don't think MPI, something that moves data when I want it to, whether it's called MPI or not, I don't really want to give that up. So
from your perspective, you talk about load store on a node rather than single copy. Yeah. What's that programming model today? What's that single load store model? Because we've had shared memory, we've had CPUs and all of that. People were using MPI on node because it was more effective than other approaches. So if we don't, I guess what I'm saying is if we don't have a load store model that works well for CPUs, do we have hope that we'll have one that works for heterogeneous node?
This is a loaded question. I think the answer has to be no to that question, but I'll let the other panelists.
All right. Sorry to pick on Tony.
Well, first get back to the first question. I think inertia is going to win the day until things get too painful. So I think, well, that's not quite true. So especially for legacy codes, I'd say we'll be sticking with MPI between nodes for a long time. There is an area, though, which I guess for this group is a message I have, which isn't necessarily a good one, is I'm not so sure how much, if we're going to win a battle for trying to use MPI for system software. What I mean by that is I think one of the visions we had with sessions, for instance, was that it might make MPI more palatable to the folks that say, gee, messaging is so much better than stream-based sockets. But then you have all these other problems. But there's so many options out there right now for people who are used to client-server programming that I'm just skeptical that if that became, for instance, getting back to this workflow managers, they'll probably be, if they want to use something besides sockets, they'd probably use something like Mochi or something that uses like this Mercury RPC from Livermore. It would be easier to use that than try for them to, I think, retrofit MPI into something, or like Google Protobufs.
Yeah,
exactly. But as far as on memory, I kind of agree. But again, I think it's inertia. Like a lot of these material science people in particular, they have their favorite codes, Lance, FASP, NW Chem, those GROMACs, and they don't want to mess with those. So if they're using MPI between processes on the node now, they'll probably stick with that until they have to.
okay. Yeah, go ahead. Yeah, you probably do. We need a mic runner.
This question is following up on probably for Tony. You commented that running MPI on unknown is definitely a mistake. So what is fundamentally preventing MPI to take over unknown programming as well?
I'll talk about E10000s for a minute. Anyone remember E10000s? It's a Sun. Anyone remember Sun? Okay. All right. So when we've got MPI stage 1.0.1 working on Sun, found out that locality in a shared memory processor worked for CFD codes much better than the shared memory because you got an owner computes behavior, natural locality, and you reorganize the code so that even though the shared memory was a little sluggish to move the data around, it was good. That's an on node. That's one SMP, half of a epic SMP node of an E10000, right? So it's like a supercomputer of yesteryear. So it actually helped you to do better than the shared memory model. But given that the shared memory models should have evolved, that's 30 years ago. Since then, you would hope to get some synergies by lowering abstraction barriers, not having to have n copies of certain data structures. Because inherently, there's a trade-off between strong scalability and weak scalability at various levels in the system. It's not all strong, it's not all weak. So I would say that I don't think MPI with n copies of the process is the optimal way to go, period. Maybe it's the fact that we have to use a COTS operating system exactly as it is, with those abstraction barriers is bad compared to and you don't like threads, so okay, maybe we need something else in the system when we're going off node than when we're on node. I just think we should not be making one copy transfers when we can have zero copy transfers on node to move large amounts of data. It doesn't seem to make sense to do that. Although there are benefits, like I said, with the E10000, with the locality you can generate if you organize your data correctly with MPI. So that's both ways.
What prevents MPI?
One copy is pretty straightforward. If you notice that Linux copied Windows and added the equivalent of a Windows read process memory, write process memory some years later, it was easy in Windows in the 90s to get MPI to do one copy. But why not have zero copy? In the 80s, we had zero copy message passing on sequence symmetries. You don't remember that machine either, probably. Okay, sorry. But anyway, so we didn't think you should copy large data structures because you could pass pointers, right? So we're back to zero copy is possible, but we can't do it. And for some semantics, it makes perfectly good sense to hand share buffers around between processes or process-like things, and you can't do that with MPI.
Do you mean the send, create, receive, destroy model? Right.
So
right.
That's just more efficient unless you
Right.
actually have to both have a copy. You choose when you have a copy rather than you're guaranteed to have it.
Right. So it's basically passing pointers around, but ownership of the data goes with the pointer, right?
Can't do it. We're good at it.
Well, so I mean, when we looked at this problem, so this was what we looked at with the Institute for Advanced Architectures and Algorithms in DOE in 2005, right? This when we were looking at many core processors, you know, my crew had this model of wanting to do all of the linear algebra out of shared memory, right? So have an environment where you have multiple MPI processes on a node, but create the data structures that you want to do in shared memory so that one of those processes could actually just drop down into a highly optimized, tuned load store math library, operate out of that shared memory. And you'd have this phase approach where you'd go, I'm MPI, I've got ranks on node, to I'm in a linear algebra library, I'm doing load stores, and go in and out of that phase to make it efficient. And the best thing that we could come up with to support that for MPI was being able to create a shared memory region in MPI, right? And it was 3+ years of work to get that through the forum. You know, just, yeah, I mean, it was just getting, you know, it started out as a shared memory proposal, which is, you know, just create something on top of System 5 shared memory that makes at least the application aware that it can do load store, right? Because if you have, that's the first step, is sort of making the app aware that it can actually do that stuff. And we had to skew it a little bit to fit it into the RMA model to get it through the forum. But once we did that, I think it's been a feature that people have used. It's certainly helped with you know, replication of large databases on node now, where people just put those in shared memory. I don't know that it's been exploited in a lot of other ways than doing that, but perhaps, I don't know.
Is it actually being used? Are you you know codes using that?
Yeah, like I said, I think most people are looking at it as an opportunity to do, you know, there are codes that have large databases of different equations of state and stuff like that, where they were replicating that for every address space that was out there. They're now doing that so that it's on a node shared by all the ranks that are on a node. But I don't think we have programming systems that are layered on top of that, right? I don't think anything else is using sort of the MPI abstractions as a layered programming for using that.
Is this sort of applying the ointment that was discovered recently? And it turns out if you use the shared memory, but you use anything but MPI operands in that shared memory, then there's no progress and there's deadlock. So the whole model has been kind of like become questioned if it can actually be safely used. So this is one of the things that come up without strong progress from MPI. What happens if you ever use, like if you do anything that's load store or a lock and it doesn't go through an MPI operation,
right?
You're out of luck. So what we still have more work to do on that model. That was sort of just like lots of these things. Martin Schultz is here, so you can say lots of discovery has happened over the last couple of years about all these kind of dark corners. To give you an example, yes, it's there, but now there's a fear factor with this progress thing, and just share that. Building on top of that now would be brought by.
Yeah, I mean, if you look at the early discussions that we had in the forum around just exposing shared memory, you know, Dave Goodell at Argonne used to remind us that the shared memory semantics, the memory model for C, didn't permit what we wanted to do. There was not a well-defined C language abstraction because you could do the same thing. If you don't go through the API, if you don't go through the language to do certain things, you don't have any guarantees. And so that was a big challenge to get the initial stuff into the forum, was just the limitations that come from different languages. So yeah, it's a mess. It's always been a mess. But you know, that doesn't stop us from doing stuff, does it? No, I wouldn't think so. We're high performance computing, for God's sake. Things don't even need to work. Got a question back there.
about like but it's unknown or unknown which are the like allows the exchange. Designation based on events. That case, should the product model address, like not all the different things that have to do with this, of this number of us. Right? So efficient. I just like to hear that. So I think the answer to that question is yes, but it's not clear to me that that's going to, the dynamic part of it is going to be something that will be handled by MPI type operations. And that, and I'm mainly thinking about these workflows I was talking about earlier. Some, especially depending on at NERSC, they don't necessarily think that things would need to be that dynamic, at least in the near future. But that I was talking with like sysadmins mainly who don't want to make their life any more complicated than it already is. But I can certainly see with these where we're sort of blending together this AI type steps with tasks which are responsible for generating data, possibly via these. I call them legacy just because they're so popular and been there for decades, that generate the data, which need to use MPI, but there's no reason why the overall workflow manager needs to use MPI if, for instance, you have an efficient parallel file system, or they may have their own RPC mechanism, which can, it's not like we're the only ones who know how to use Ivy Verbs or libfabric or UCX or any of those. It's some software that uses that and is able to more easily do things dynamically. Like when Julian was talking about the endpoint IDs today, well, lots of software already does that, and we didn't do it. We have communicators in ranks. So I think there's definitely, although it will be challenging, I think there'll be some environments where there are workloads that will benefit from being more dynamic, but I'm just a little pessimistic that MPI is going to be providing the answer necessarily to supporting that, at least in overall workflow.
Yeah, I'll just say that MPI does have a dynamic process mechanism. There's a chapter in MPI called Dynamic Processes. It's been there since MPI 2, so that's 1997. And so there is a way to expand a set of processes by spawning new ones, and that becomes part of your MPI communication framework. And there's also a way to disconnect, so you can separate them. It turns out to not be used as much. And on some of the vendor, the HPC systems, it may not be supported because it doesn't match their scheduling or resource management software. And again, their users on those HPC systems don't want it. They want that they ask for the fixed process count model. But on clusters and with the open source implementations, you can use that. But it still has an MPI flavor. It may be you probably, there may be other systems that do it in a more that's what they do, and they do it more easily, or that's their whole mode of operation.
So some thoughts of that, Sheikh. So in MPI 1, when we define the groups, the context, and the communicators, we designed by committee. And at some point, when we decided that the context model would be closed, we didn't make it easy to share, let's say, or serialize communicators and share them with processes that were not related. That was an intentional restriction that was placed on the design. So one of the design points was to make those things open so that you can, in fact, serialize and ship information about groups, contexts, and communicators to new participants and let them res those. Sorry for the, that's a old word. You could put them, you could reconstruct them or deserialize them if you prefer and make a distributed computing model. We struck with the strictly static group and context model. Context is actually ineffable. You're not supposed to know it's there, but we got so long in the standardization where I was writing about context that the word's still there, even though it's not anywhere visible in the API, right? It's a hidden thing, a communicator. But why do we have a communicator? Lexical scope and spatial collaboration, right, for groups and allow you to program in the large. That's what our goal was with those features. It was never our goal, and MPI 2 with dynamic process management was supposed to allow you to grow them. And even though you make the single assignment objects, which is, by the way, a very important feature, that their communicators are essentially single assignment objects as are and groups, and then you make new ones, or you can think of that as a really virtuous object model. But no one would let us use the dynamic process model because they said their LSF or whichever schedule they had wouldn't play nice in a back scheduler mode. So no one ended up using that. So we lost at least even our rudimentary ability to grow and make dynamic processes then. And so no investment has been made there at all. By the way, it's really ugly in some areas to play with intercommunicators.
So just out of curiosity, I mean, so what was the heterogeneous motivator for the question, right? Because this is, the dynamic workloads and process creation has been around since, was there a particular aspect of heterogeneous systems that was motivating that question? Right. 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 Okay. Right. 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 Okay, so for you guys online that just missed all of that, the answer was thinking about the broader cloud community and hyperscalers and the fact that they're running complex workflows that are going to be highly dynamic and wondering whether we can, whether that's influencing what we do from a programming model standpoint for MPI. Right. Looks like we have another question.
Sure. Well, to continue that trend, right? I'm from Amazon, and there's smoke on the horizon of the ships coming of this dynamicity, right? It's easy for us to give you another 10 nodes, whatever. There's no scheduler that interferes with that anymore. And more HPC loads is coming into the cloud, right? So this kind of trend is just over the horizon. So we need to start paying attention to it. The fault tolerance aspect of this, the dynamicity, the asynchrony, all three of those are probably big components of the future here.
I'm going to try to get Shake's question to actually have a heterogeneous piece to it by saying, when you have hierarchical, you can have disaggregation at some scales in the systems, right? So you can decide what to deploy. You can actually put your nodes together at certain scales in racks, and therefore decide how heterogeneous or how you compose your nodes within limits, right? Now, that may not be optimal for every HPC application, but it seems like a really great idea to explore. So if you have a GPU or not, or you have two GPUs or not, heterogeneity is also part of the scheduling decision of how to compute, where to compute. So I think we can speak to the programming models. I might aggregate nodes with certain qualities based on their heterogeneity. There's a piece of your question somehow having to do with heterogeneity in there somewhere, Sheikh, I'm sure. So, but I think what's pretty clear, pretty clear that the general area of dynamic is something we can solve. We can solve those problems, but they're unrelated to what we were supposed to do.
All right. Anybody else? Mark.
Thank you. I want to go back to the dark corner part of MPI that Vince Tony referenced that so nicely. So we have found a lot of dark corners, and shared memory was one of these things. But they seem to be particularly happening when we talk about combining different runtime systems together. And that will happen more and more in the heterogeneous world, right? We have one big issue right now. We look at OpenP. Should MPI follow the MPI OpenP semantics or not, even though they're two separate standards? What is the link between the two? You're thinking about adding CUDA and SYCL bindings to that, right? So we're going to drag in some of that semantics into MPI as well. So how are we going to avoid the dark corners if we go down this road?
I'm not going to answer all the questions, but Martin, there are many dark corners as we've discovered, but I think that's because we're trying to improve the product, right? So you find issues, but fundamentally, unless there's a common understanding that the process is not having, or the user program doesn't have to intentionally devote resources to a library for it to do work, that there's a synchronous notion that each library has assigned resources and makes progress and does what it's supposed to do. Fundamentally, they're all coroutines. So it forces the application decide how to schedule all its libraries that are providing services to it. So as soon as you put a few of these together, you're playing a game of forcing the schedule to come to the highest level instead of being in a commonly shared runtime system that also allocates resources either preemptively or cooperatively or some combination there. It's a broken model. So the whole idea that the weakest model that's beautiful for MPI specification and made people very happy over the decade is not a good way when you combine things with other things that also want to have resources and don't want to wait an arbitrary period of time till MPI decides to finish a call or a user decides to call MPI before something else can happen. So somehow you cannot have the beauty of the specification weakness at the same time you have composition without getting deadlocked at some point, like this shared memory thing. But you're going to find that everywhere. Things have to be able to have a certain quality of service or type of service or guarantee that's independent of what another library is doing, or you're going to get stuck. And so but our specification folks like weak progress for specifying things. So there you are. And Rolf's probably on the phone. He's probably going to argue.
Well, it is a mess. I think just like Julian's was talking about one idea of how to get around it. I think we've just been lucky that, or at least that no one's complaining, or at least, well, that's not true. I think we're just gotten kind of lucky so far, and users who have applications that have all these complicated components are smart enough to be able to manage it. I'm not sure I understood exactly what you meant by convergence or OpenMP/MPI specifications being interoperable or something like that. Oh. My first thought would be no, but that's probably wrong.
Well, MPI has tried to avoid saying anything about a specific other model. It talks about threads in general or shared memory in general, and perhaps for GPUs it would be not CUDA specific or any other vendor specific about streams in general or something like that. And that might be one way to, but there might still be some dark corners or, like the shared memory, there's some things are iffy there about the memory model and so forth.
So
as a follow-up, this is the right way forward. Why do people lose should go towards kind of feel what's it possible about?
So the question, so let me repeat the follow-up question. It was, say it again. Should we continue to go down this path of interoperability with runtime systems to find those dark corners, or should we go to some other alternative?
Yeah, should we remain generic, or should we go specifically with OpenMP or SYCL or CUDA or stuff? So I would say staying generic is preferred, but unless we find that we cannot stay generic and it leads to problems or the solutions that are not good, then maybe. But I would prefer to avoid that.
It's really hard for me being the moderator of the panel to not be a panelist. I'm struggling with this.
Certainly not for something proprietary like CUDA or even something reasonably generic like SYCL or HIP or something which is fully generic like OpenMP. But what you do need is something that's kind of alternative concurrency mechanism independent, which is you need to have things stated in terms of your expectations for memory fences and things like that. If you have to have a clean memory model on the node, or else there's going to be problems. And as long as you have that, then you should be okay with any well-designed alternative.
So I think your challenge comes when you start. The fundamental question is who owns the resources, right? It's OpenMP owns processes and address space and also devices. MPI thinks it owns processes and memory, right? You get into this discussion of composable programming systems, get conflicts for sharing resources because they think they own everything. If only there was something that owned all of the resources and that was persistent and handed those resources out based on how they were being requested and was able to mitigate those kind of things and do authentication and other stuff. Like if it was operating in that kind of system and it did things in an intelligent way, that might be an alternate solution. But to this point, we have things that don't do that. And so we have to solve them at some other layer. We try to solve them in a programming system layer when perhaps the thing that actually owns all the resources and is there all the time might be better at how it manages those across the programming systems. So sorry, I have a hard time. Of course not. So what memory are you getting to on a node that doesn't go through the OS, Pranas? What memory on a node are you getting to that doesn't go through the OS?
Allocating it or actually operating?
Both.
Operating on it is down at the hardware level where you have all the fences.
What hardware are we talking about? Nothing is running on your GPU that's accessing memory that didn't get. So I'm saying you can allocate memory to manage. Once that memory has to be allocated by the operating system in order for you to use it. Once you get access to it, you can use it however you want. Right? What you're saying is
that allocated memory is shared between MPI.
How did it get shared? Because the
programmer says, here's the data. In the private world, then I want to use it.
Yes, but it got shared because the operating system let you share it. You don't get shared memory on a node without going through the operating system. You don't get shared resources on it.
System 5 shared memory. I'm talking about I'm in the same address. Because I'm in that address.
And I don't know how you got in that address space. And what's really great is this: people online have no idea what the other side. The other side. This is a perfect argument to have with Bronis because nobody can hear the other side of it. All right, sorry, I didn't mean to take it that way. I still think all the shared resources on a node are managed by the operating system. Anyway, do we have other questions about heterogeneity in programming systems, programming models?
So this, goes to the question of heterogeneity on the node and, around the node with the smart things and everything. So again, with MPI, so far for the last 30 years, we had a very simple programming model, MPI, and where you needed threads, you would do threads, whether it's OpenMP or pthread. So that was it, right? Now we have a whole bunch of other things to do with it. It's not just MPI, it's not just OpenMP. SQL. So there's all these other things that are there. And particularly, all of them are making decisions, whether it is resources, memory, or whatever the case may be. So, so far we have been successful by saying generically threads in it. And we have managed to keep it that way. But the question is, can we continue along that direction? Or do we have to now start going and saying for each one of these new things that are emerging, there is a separate path to go, which is not obviously what we would like to have. We would like to keep it this way, but will we succeed if we try to keep it?
That was Martin's question, right? So that was also Martin's question: that do we need specific per programming model or whatever per X solution or generic? And there's no end to the X if you try to solve one after another. So to try for the generic unless it really causes problems and unless it's completely unavoidable, I would say.
I would be in favor of lowering the cost of portability. This is a model that's going up, right? So we have MPI programs, but we think that being completely generic is very expensive. So we had a talk at one of the many meetings I've been to over the years, and someone said 2% of their code gets rewritten, or 3% to support some new supercomputer. They rewrite some kernels. They have a new GPU. They tweak their MPI approach, and their application works. So the claim was that it's a piece that's not really performance portable. It's the performance piece that's not portable, but they have control over the overall cost of their software. I just wonder why I can't have a détente between product A and product B in a small areas where it really makes a big difference. And the rest is still completely generic. And the answer is, if you do it, this is how you should do it. If you implement it, this is how you should implement it. And so it's still reviewing a normative expression of what's valid within some range. But if it is like CUDA, I'm programming CUDA, and I have the little appendix that's how CUDA works with MPI. I think we have a very good example of that for many years, Fortran programs were illegal with asynchronous messages in MPI. And they just happened to work with most compilers until they actually created new keywords in the Fortran language, which make it possible to have asynchronous buffers so that MPI could work correctly. There's actually like a treaty in Munich, I believe, in 2011. That was signed to make this true, and it now works. And you have to use certain extra keywords because it was possible to have copy. And I'm sorry, Bill Drop should explain this deeper version of. You basically can copy in and copy out. It's not called by preference, and so you could effectively never be able to have an asynchronous. I sent work, not receive. Sorry, not receive. So keep that in mind. We actually had to go between two different standards to make that standard, and it's very specific in both sides.
Another question?
Yeah. I don't want to circle back the discussion, but I was thinking about the role of PMIX in the coordination between programming models, like having our common runtime environment for different programming models, and use PMIX functionality to coordinate those programming models.
So I could say that's certainly an option in some cases. A lot of us are using that, an implementation of the PMIX standard, let's call it that. I wouldn't want to put my hat totally just on one solution, but it has, it's an approach that I don't think it addresses, it's not going to handle, like, for instance, if there's some, and probably it isn't obscure, some, well, actually know of some OpenMP, and particularly OpenMPI, like in terms of some specific problems, which wouldn't be solved by PMIX. But in theory, something like that, if everyone was using it in quotes, and it was being used in a particular application, it could be kind of the czar that could help with managing resources, particularly things like binding in a sane manner. But again, that's just one. There's a standard, and then there's effectively mostly one main implementation of it. I'd just be nervous to put all the eggs in that one basket. I don't think they're suggesting that, though.
I spent a lot of time about 20 years ago making something called MPI-RT. And many of you might have participated voluntarily or otherwise in some of those meetings where we were working to provide actual quality of service. It was very difficult for the operating systems to provide us with any quality of service or end-to-end guarantees in the network. And ultimately, it was a very fast API, but very hard to program, and it wasn't well adopted. It was aimed more at defense multi-computers anyway. So, but we learned a lot from that. One of the things is you need to have some kind of quality of service if you want to get some guarantees. So if you want OpenMP and MPI to both use your cores and your threads in the application, you might want to have some common control over how many resources they get and when they oversubscribe and when they don't oversubscribe, or how to make trade-offs. And I don't like priority-based models, but in some sense, priority is the weakest form of some way of saying, I care about this more than something else if I have to make a nasty trade-off. But without those kinds of things, everything is sort of a guess. You have no idea what's really going on until you do profiling, and maybe it's not what you want, and you can't make it be what you want because you have no control over quality of service, not the individual components. Certainly the application can't mandate how the threads, other than OMP num threads, okay? What does that do to the MPI? Not sure. So I think we have to look deeper at the runtime system. The PMX thing goes between those, I guess, and it doesn't. We also have to talk about the scheduling, and you have to start talking about some sort of quality of service. It's highly controversial because that requires to do some hard things, and quality of service might mean different things on different systems. But I think you have to look at some sort of QoS if you want to have some guarantees.
Yeah, so I'd say at the PMIX level, yeah, probably there is room. And for the most part, PMIX is sort of hidden from the application developer. They call MPI or OpenMP. They don't see PMIX directly, right? That the MPI implementation talks to PMI or PMIX. So there is room for such things because that those are sort of expert library developers who can deal with things like that. But if you expose it to the end user, then the question becomes, what's the API, and does that become part of some standard, and then it's carried forward, and then all those complications begin. But at the PMIX level, there's probably room for doing things.
Okay. Other questions? Puri's got another one. He's the new runner.
Sayan has agreed to be the runner now. Since I started asking questions, he said I will be the runner. Okay, so in my last 2 decades plus teaching experience that I have taken the parallel computing course, so till the last few years, people who have taken operating systems and computer organization, not computer architecture, but just computer organization. And I could teach parallel programming for them. I would do, threads with OpenMP threads first, and then. So in the last couple of years, I'm really finding it hard to teach. I could teach the same old parallel computing course, but that's not what students are interested in. They want to program the GPU. Okay. So going forward, what kind of a preparation do these students need in order to learn parallel computing? Because they now need to know about the GPU, they need to know about the smart NICs. Where are they going to learn all of that? And don't tell me that I had to teach all of that. That's me.
I would say you need to have a 4-node cluster for your class that has CPU, GPU, and a network, and you have to tell the students that the parallel computer is all of these, and you need to have a on-node program that takes advantage of the GPU as well, and MPI across nodes. And they may find MPI the easier part, the GPU and getting performance out of the GPU with CUDA or anything else, maybe the harder part. And you don't need to teach them all of CUDA or all of OpenMP or all of MPI. But if they can write some code that uses all of this, I think they'll feel that they at least understand how it works and what needs to be done, and then they can take on more complicated tasks later on. Yeah, they need to understand GPU architecture. For networking, they can understand it at the MPI level, that there is how to use the network, and you can use MPI for communicating across the network rather than getting into the lower levels.
Oh, I think systems are more complicated than before, right? Because you haven't really had to teach anything about the network except what is the zero message latency and what is the asymptotic bandwidth of ping pong or streaming. And you could say a network is an abstraction that everyone talks to everyone else. By the way, they may not all talk to each other equally well. You can test that in your test program, right? And effectively, there is topology, but not maybe in the small test system. You can't see it. You had to teach a lot of things before. We just got to skip over a lot. The GPU class by itself has a lot of content in it, right, to do that well. What did we do before that? Well, some of us decided to teach people how BLAS worked inside. What is vector assembly language on an x86? Or, why not? Why shouldn't you understand as a computer scientist how people make these processors actually get performance? That's not real popular. That's painful. And CUDA, in some sense, or the other programming notations that are about, long vector machines. Okay, you're learning something at a much higher level now. But really understanding what's going on, you still have to go into that architecture and explain to them. And real performance involves lots of bit and performance counting and understanding really deep things that work differently on every GPU version. So yeah, it's a hard problem. So either you can go for sort of a breadth-depth trade-off, say here's intro to parallel computing, you learn a little of everything, or there's more parallel computing classes. I don't think you can get away from the fact that, if you look at a vector assembly language, a vector compiler, for example, all you need to know is it's multiples of 64 with double precision or numbers. Try to keep your loops to multiples of 64, and something might happen bad at the last, there's only a few rules 40 years ago once the compilers could do vectorization. But look at vector assembly language. It's extremely hard on x86 64 machine to do that well. You can show them a glimpse of that, but none of them are going to program a CUDA or something like that. Lets them learn, but they're still only learning a glimpse because people are serious about that. They're doing some really awesomely complicated things to get full performance. And that's an expert level, and you're not getting it in your first class. So I guess you have to do a breadth-depth combination, and those who want to learn more take the next class and do more practice and do more experimentation. And the code certainly, by the way, that code's not performance portable. It's portable. You know very well that every time we write a new GPU, we should write the kernel again. You OpenCL for sure, right? I know I can write the OpenCL. It's meaningless performance-wise. But even CUDA, you change what you do in principle as you go from GPU to GPU. certainly with the compiler produced is completely different. I have to say there's a deeper problem that performance portability is getting harder. There's a lot more to learn. I guess, sorry, more classes, more credit hours. For those of you not in academia, we have 120 hours plus minus each an undergrad degree. You don't get more.
Barry, I'm going to answer from the perspective of someone who has dealt with a series of interns over the past several years. I've never had to teach at an institution of higher learning, so I can't approach that. But I would say probably the breadth thing is I would suggest. I have had students who had never used a GPU, but they knew how to program and they knew what the Linux command line was, and they were smart, and it didn't take them long to figure out if I wanted them to try and get something going on a GPU, what they needed to do for that. But if they didn't know how to run the command line and they had never programmed anything except maybe Julia or something, then it was kind of challenging. So, and that doesn't mean they have to learn Fortran.
I just wanted to say that I think what you said is a very good point. There has to be, we spend a lot of time making sure everyone can do Linux and understands Git and understands how to compile and things that are like the basics of being a system programmer. And then, within the first parallel class could touch on several topics just like it has before. But you can write a simple GPU kernel, but there's so much more. So I guess I would say parallel computing 1. There should be like hands-on system programming 1 followed by your class. That's what we have to emphasize. No one can do anything before they can do the basic system programming.
If you can do it on a robot, that would make it even better. Then I'll be excited. So like MPI programs on a Raspberry Pi robot. And better yet, make it a submersible.
Another question back there. And just while we're waiting, Howard mentioned this language called Fortran. I don't know if you guys have heard of that. Oh yeah, take a poll. Raise your hand if you've actually written Fortran code in your lifetime. Okay, that's
you
6 of us.
Whoever has gray hair or bald hair, they probably programmed it Fortran. But Puri, I think the problem is even more fundamental and deeper. So we don't teach or mention about parallelism and distribution is everywhere. There is no device right now which doesn't have multiple core, which is not connected. And if you look at the way we start teaching computer science, CS1, CS2, CS3, is the last century model, right? The time is linear. There is one memory, one processor. Students learn thinking sequentially. And then suddenly in senior year operating system class, they see synchronization, asynchrony, concurrency. And by that time, their brain is hardwired, right? So we say that we need to teach the foundational concept, concurrency, right? What is concurrency? You need asynchrony. These are fundamental properties of modern hardware. And we need to, those concepts may not be that we have to write code. They need to think parallel, code parallel. And there has been effort going on, and in some institution, in my institution, we do actually parallel distributed computing. Very fundamental. Actual concept, unplugged activities and others, actually in CS1. And student gets it. They see the world is parallel. They do things in parallel. They play with cell phone in high school, and they see two things, right? They are clicking on this one and doing something. So they have the innate notion of concurrency, event-driven, all this. But they come to CS1 and we teach them average these 3 numbers and all those things. Still, von Neumann model is the guiding principle until senior year, right? And then we all learn parallel programming in graduate school. At our time, there is nothing in undergraduate. So I think fundamentally, we have to start teaching the foundational concept of parallelism and distribution from CS1, and we need to figure out how to do that. And I think it's a deeper problem. Obviously, then once they get it at the sort of first 2 years, then you can introduce CUDA or other advanced concepts. So right now in parallel programming class, which you teach as a senior class, I teach too, we start with this thread and some of the fundamental things. And you don't have time to actually get to some of the advanced things.
Along similar lines, can I add a quick point? So Andrew Lumsdaine teaches a parallel programming class, and his opinion is that the methodology of how you are teaching it, if you teach it using a composable programming model, then that is better. So his version of composable programming model is, of course, C++, right? And he tries to use C++ in teaching elementary parallel programming that touches on GPUs, etc. But from using the C++ concept and recipes. So I would like to know your opinion.
I think that's a great idea, if he's doing that in the context of MPI, why aren't they using MPI for Pi?
Yeah, he wants to use C++. So he has been using the bindings, and he still it's useful.
No, there's something. Is it MPL? An intern who's just digging into that. Could also use Rust MPI bindings.
MPL is another.
We've been looking at that some, and I think that'd be. It certainly is a lot better than I would not be wasting time with the ancient, deprecated, thrown out of the standard MPI++. I mean, we haven't taken an extensive look at it, but it looks. I mean, it reminds me of what I see when when I see people writing MPI for Pi, which I think is probably most MPI code is written in Python nowadays, new code. That's my opinion, based on nurse experience with users.
So since we're talking about old friends, I'll bring up Chuck Seitz, and he was doing really cool things in obviously multi-computers for the last 10 years. He said, remember, the parallel algorithm is more fundamental than the sequential algorithm, and you should be learning algorithms. You should be understanding the sequential algorithm is a special case of the parallel algorithm, not this other process by which we through some sort of stepwise refinement, we figure out how to remove the restrictions of sequential and make parallel. So all through curriculum in computer science, this goes back to Shake Note. Fundamentally, you learn mathematics sequentially. You do recipe A, B, C, D. There's your proof. You think everything's sequential. If you've done more mathematics, maybe you think you're more ready to do computer science, but okay, whatever. It's clearly the parallel algorithm is more fundamental than the sequential algorithm. So learning that model, that can happen very early. It can happen. By the way, Alice did some things that look very concurrent in them, unless you were explicitly being sequential. Obviously, it wasn't implemented necessarily on a parallel computer, but it was teaching fifth graders how to do things that look awfully concurrent, right? Ray tracing or drawing pictures with Alice. But just keep in mind, if parallel algorithm is more fundamental than sequential algorithm, pedagogy has to reflect that. But you have to teach someone something. You have to start somewhere. So it's clearly also a spiral model. Everything's converted to the first day. But also remember computer science from years ago. Scheme and Lisp. Applicative languages, things, or just think make if you prefer make. There's an imperative piece and there's a non-imperative piece. That's the part that's really figuring out. Those kinds of programming languages, most advanced computer science, undergraduate, very good teaching. Those kinds of languages where there can be concurrency, there can be massive parallelism, and all those things are. I think you stick with the idea that you want the people to think parallel algorithms. That's the pattern. That's the pattern.
So we mentioned the C++ bindings, and Rajiv, you mentioned deprecation the other day. Is new bindings for languages a good place to start with deprecation by not binding certain features into these new languages? Like a new C++ binding that doesn't bind synchronous send.
No, I think we should first mark a function as deprecated before not giving it a new binding, because then we're picking something to not have a binding when it's there officially in the standard. So the way that with the C++ bindings, when they were deprecated, the new MPI 3 functions didn't get those C++ bindings, and then the C++ itself were removed. So deprecation is the first step, and the removal is the next. It happens in the next standard. But I'd prefer to be careful about deprecating things and then not giving them the new bindings, because otherwise you're picking something and which is officially there and not without a binding.
To be clear, the elimination of the C++ bindings is an example of something the MPI forum did quickly. Now, if you want to deprecate something, let's say you're lucky enough to convince the committee to let you deprecate a function, then you will be able to remove it through the next major release. So you're talking about a third of your career, probably, to get rid of something at this speed that we're working. Clearly, we're going to have some more serious look if we really want to focus people on new ways of doing things, to tell them very seriously, deprecated means don't use, and you better be working on your code renewal to get rid of this stuff, because we're telling developers of MPI libraries, don't bother with performance on these things. These things are going, but it's glacial to get rid of things. I was very impressed in Fortran 2018. I can't do common blocks anymore. I was very pleased that they're gone. Equivalences, all that stuff is gone. They actually got rid of some stuff that when you grew up, if you actually did, the 5 of you do Fortran know this inside story, that those things are like bread and butter up till like at least 10 years ago. They got rid of those horrible constructs that were inimical to good programming, but it took a while. MPI is slower probably than the Fortran standard. We might not meet regularly. It might take eons to get rid of things. All that time it has to be supported by the production implementations and all the vendors, and that costs something even if no one uses it. Or worse, they use it and we're trying to get them to use something new. So we have to learn we actually have to run a forum that runs at the speed that's compatible with the other kind of development going on in the world, where you get rid of things, you add things. Good work, Beth.
So backwards compatibility, right, is essentially what you're talking about, right? You're talking about reconsidering the MPI forum's approach to backwards compatibility, right?
So I have maybe a little provocative question. We arguably have lost the race when it comes to accelerator support, right? There's no vendor communication libraries that do that much better. What is the value proposition for MPI in 10 years from now? Right? How do we prevent users from just going to proprietary communication libraries, especially if what Ron said, we're moving away from government-sponsored open systems to cloud systems where there's one or two vendors who have full control over the whole software stack, right? MPI is an open model working at a glacial speed of development, might just not be able to keep up with that. So what is what value do we bring to the table in 10, 15, 20 years?
The easy one is inertia of the apps that even if they're on the cloud, they're going to be running. Not that that's a particularly easy answer, but that's the short one. No one's going to rewrite lamps unless they. No one's going to rewrite lamps in a way that's only going to work on one cloud vendor's platform. That doesn't mean that we don't have a keeping up problem later on. Like obviously you're talking about nickel and stuff. But, that's one thing. And of course, at least with one particular vendor. They're very active in one particular MPI implementation. Sometimes they aren't enjoying that interaction, but I think as long as they're customer driven, and as long as their customer says they have an MPI application to run there, they're probably not going to spend a lot of energy trying to convince them to rewrite it. That's what I've been told by at least several people who work at AWS. And I'm not picking on them, but they're customer focused. If the customer wants MPI, then they'll support MPI.
Yes. If the application is viewed in big places, yield the power of the customer in a fairly unified way. Want to keep doing this, make it faster, better, better.
So disruptive technologies are neat. They start, this is a business book thing, so you don't have to believe it, but you can look it up. Basically, so what does a disruptive technology do? It starts out below the expectations of the market. And then at some point, it has something better that the customer wants. So it exceeds the expectation of the market. It might be cheaper, it might be faster, more scalable in our case. And then everyone mercilessly abandons the old thing and jumps to the new thing. And that's how other things that are not constrained work. So when at some point you lose, let's say MPI is no longer portable, or MPI is 10 times slower than some other thing that's out there. This disruptive technology, like for example, some people say, "Oh, MPI is dead. Hadoop is here." That was an example of a candidate competitive, disruptive technology for MPI. I don't think that happened, but there could be something better than Hadoop that does that. And everyone will mercilessly abandon MPI, and they'll go to this new thing. So the goal is to invent the new thing, right? So invent the new thing. All right. Well, maybe it still has some connection with MPI or it doesn't, but that's how disruptions work in the market. We have not been able to figure out how to disrupt it, nor has anyone disrupted it for us yet. So eventually that could happen, but that's how MPI will be, disrupted. Again, by the way, it'll be at that point valuable to rewrite lamps in this new thing because it'll be such an advantage that the cost of doing that will be outweighed by the benefit. And that's an example of how there's adopters decide to abandon MPI. So you have to find that new technology that has those properties. And that's been elusive for 30 years.
Oh, there is. So this is from Jim. ABI compatibility is a huge issue for containerized MPI applications. When you need to pass through the system MPI library, the containerized application may not be able to link with it because of ABI differences. So I guess he's talking about, what's the situation with ABI compatibility? This came and went in the forum a while ago. I told Bill Gropp I'm surprised this issue has not come up again in the context of containers. I'm not surprised I wouldn't be surprised if the forum avoided it again, but I'm just surprised it hasn't come up. Do you guys have thoughts on ABI?
I was going to jump in if you don't mind me coming off mute.
Yeah. Go ahead.
Just, we have a whole container catalog, NVIDIA does, called NGC. And we just full on have a problem how to deal with MPI in these containers. So like this discussion about, disruption and, adoption of, cloud and stuff like that. It's from where I sit, it's already happened. And we've got catch up work to do in order to be able to produce an MPI that is viable in such an environment. And I think this is just one example of where, why users really can't use, to put it bluntly, can't use MPI if they want to have a container that's actually portable, as most users of containers would want.
Okay. Do you guys have thoughts on that?
So our Charlie Cloud container group at Los Alamos wrestles with this. First of all, I think there's just an engineer, at least with the, I won't speak totally for MPitch, but I know they did come up with a standard AB, supposedly between the vendor and the mainline MPitch, so that there was an ABI compatibility. So I don't view this as a fundamental problem. I think it's an software engineering problem that just have to exercise some discipline. And unfortunately, in OpenMPI, we haven't been that great at that. We may get better at it. The way, in particular, that in Charlie Cloud we're trying to solve this problem is the layer that's network specific. For instance, assuming you fix the MPI ABI compatibility problem, which I don't think is a fundamental problem with MPI, is you make use of the fact that most of these newer network interface packages have notion of plugins. And so I know, like, for instance, Charlie Cloud is working with CSCS on a solution with the Fabric, where they have multiple plugins, and only the plugins are loaded at the bottom that are compatible with the underlying network that the container is sitting on.
If I could respond to that, I think challenge that we have there is that we don't have a standard across the whole industry for what that lower level networking layer should be, right? We've focused our attention on UCX. So I think a solution that's based around libfabric is probably not going to solve at least the problems that we need to solve for our users.
No, UCX you can also do with UCX the same thing with plugins. I would keep wanting to look at it. I can't see it.
Well, no, I agree with you, Howard. But then the trouble is that UCX doesn't cover all the networks.
That's right. So you may have to package in your container both the UCX and a libfabric and have an MPI that can switch back and forth between using one or the other.
So one solution that has looked potentially workable is to use a shim layer. There's such a layer called WI4MPI, basically uses the tools interface so that you can put this shim in between the application and the MPI library, and the shim library can be recompiled so that you've got versions of it for each of the different MPI libraries. Right, it's kind of a band-aid for not having ABI compatibility. You introduce something that can essentially give you a wrapper around the MPI library so that it can work with the ABI the application was compiled with. I'm sure there will be performance impacts of using such a solution, right? There's probably hash table lookups and so forth to translate handles.
Yeah, and this ABI compatibility issue comes up every now and then. And in MPitch, we do maintain ABI compatibility, right? Between versions and with the vendors, and we don't willy-nilly break ABI compatibility. Is that correct, Yanfei and Hui? Yeah.
I think this is true of all of the major MPI distributions, right? I think OpenMPI and Cray MPI and so forth, Intel MPI, all kind of have their own, internally consistent ABI. But the trouble is that, you take lamps, as example that was given earlier. If you wanted to run it in the cloud, you have a container with, the whole lamp stack. It's compiled against MPI. And you want this container to be portable to run, with, to run on, let's say a Cray system one day and on an InfiniBand system the next. Achieving that portability is a challenge specifically because of the MPI library on the Cray system not being ABI compatible with the MPI library you would choose for the InfiniBand system.
But is the rest of the software compatible? I mean, can
Yes. Yep, it's just us. we're the sticking point, unfortunately.
But is it a problem, Jim, it is true that MPitch and the derivatives, I can speak for Intel MPI, it is ABI compatible, right? And that was a few years ago, and I think it's something that we've been respecting. So is it that the other major implementations like OpenMPI are not ABI compatible?
I don't want to. I think pointing fingers is a very.
But it doesn't matter. It's a problem. Is it? You mentioned something. What I want to bring is it a problem of the OFI or is it a problem of the MPI implementation itself?
The MPI standard does not specify ABI,
That's correct.
This allows implementations to make different choices. So the handles are represented differently between MPitch and OpenMPI. And MPitch makes, some optimizations, by placing data in the handle value itself. OpenMPI, I think, uses pointers. The representation that you have for the handles guides you toward, one range of implementation choices and optimizations versus another. I think they're both, from the MPI standards point of view, I think that they are both reasonable choices, and we give implementers permission to do this. I'm just here on my soapbox raising an issue. I'm not trying to. I think solving the ABI problem is a challenge, and I think it's worthwhile for us as a community to try to take this on. And I don't want to propose that we adopt one set of ABI or another. I think it's something we need to have a community discussion about.
It's a community effort, right?
Yeah. Yep. So like I said, the MPI forum had these discussions 10 years ago. We had a strong proponent from Microsoft pushing the committee to have these discussions. I think the discussions went on for more than 2 years around the challenges of ABI compatibility. All right. Sorry. Yeah. Well, maybe I stopped going after the 2 years and they kept going.
No, we did. Like, I remember, why am I drawing a blank on the person from Intel that was driving? Pavan was quite involved. We were driving from Argonne at the time, trying to get to ABI compatibility.
Yeah. All I'm saying is it wasn't successful. It didn't really, we had lots of discussions. It didn't really go anywhere. And I agree with you. I think what's going on in the virtualization space and containers is we should have that discussion again and see if we can make progress on it.
I think it was successful in the limited way that Maria described. That an outcome from that was that we achieved ABI compatibility for MPitch and derivatives, but right. we didn't manage to get there. That's
not. Yeah, that's an implementation. That's not really ABI compatibility.
Use the same implementation.
Yeah, that doesn't. Yeah.
Yeah, but this is just, Jim. This is a social issue, right?
I think there are a lot of technical issues that are wrapped up in it, though, right?
Right. Okay. So, hypothetically, and I cannot do this. I'm just presenting a word picture. Okay. If I gave each implementation $1 million to go do it, would you go do it? No. You would.
I would take your money. Sure.
Sure, you gotta get everybody, right? You can't take it individually. You got it.
Oh well, no. Harder.
You $1 million, and you $1 million, and you $1 million. I can't do this, but I'm just saying, right? Would you go do it?
So I think the reason why I kind of chimed in here, this has been on my mind, right? And I saw an opportunity to try and just raise community awareness, and I'm really glad to hear the response that I'm hearing from everybody in the discussion. So how can we go get to work on this? Should we form, for instance, a working group in the MPI forum? Is that the right place for such a discussion to happen?
Well, we had one of those before, right? We never completed that working group. But my question was going in a similar direction. Yeah, the comments were always, this is necessary to achieve performance and give freedom. But how much? We have OpenMPI and MPitch right on the panel here. How much benefit are you getting from your perspective, ABI, or is it really just not willingness to change to something else?
Sorry, Martin, was that a question for me?
No, Jim, the question for you would be, how much is NVIDIA willing to move to libfabric instead of UCX?
Oh, but right? What does that have to do with ABI compatibility for libmpi.so?
It doesn't, but what it has to do with
but it's a wrong question.
Let me finish. What it has to do with is everybody's trying to differentiate, right? At some point you have to pick how you're differentiating from your competition. OpenMPI has picked a way to differentiate from MPI-CH. NVIDIA has picked a way to differentiate from. others.
We're trying to solve requirements that
Right.
and so the problem we're trying to solve here is that anything that costs outside of the virtualized environment needs to that.
Right. So you can't hear Branas, can you?
No, I'm sorry, I can't hear.
So Branas was talking, and he gave a really good answer, Jim.
Okay.
The entire room is agreeing with Branas because it's after 3:00. And so, unfortunately, you brought up a really contentious issue when we were just running out of time.
So if I could just say
into the break.
Yeah, I'm sorry, Ron. If I could just respond to the point that you made really quickly. The application's problem, their linker problem, is libmpi.so. It's not further down the stack. Whatever's behind libmpi.so.
I understand that, Jim. My point was picking where you want to compete in terms of differentiation. And it's a similar argument in terms of being where you want to draw the line to compete. So, all right, let's thank our panelists.
So, Jim, what I was saying was that your point is exactly accurate, and it's that you're crossing the virtualization plane, right? And right now, the only way that is provided is to use a consistent ABI. But the real problem is that the problem you're posing is that the requirements under which MPI was designed are no longer consistent with the requirements that you want to have satisfied, right? Which is using it in virtualized environments. And so the fundamental requirements you're posing for MPI are different. So that requires rethinking in some way. And the idea to have a consistent API is a perfectly reasonable way to go about it. But that requires like rewriting huge amounts of software for one or the other or both implementations, right?
Yeah, I agree. I think you've stated it really nicely, which is why, we're investigating things like having a shim library that, can itself have different versions to wrap and provide portability. But, I think I think we discuss these things like MPI and cloud environments. If they're really important, I think to us as a community, then I think that that MPI needs to be serious about taking on the requirements in order to be viable in that environment, which requires that we support containers.
I think you're exactly right, and since containerized environments are almost certainly going to be commonplace even in what we think of as HPC systems, traditional HPC systems. It seems like a fundamental problem that the MPI forum should take on. The interesting thing is I didn't feel like, while people agreed with you that it was a problem, I didn't feel like they agreed with you that it was one that they had to solve.
Well, yeah, that's where we tend to get stuck.
Oh, well, yeah, I thought that was an interesting point you raised. Thanks.
Okay. Yeah, thanks, Brothers.